Diazonium salts. Introduction. Arene diazonium salts were discovered by John Peter Croises in 1858. They have the general formula ArN2X, where Ar stands for the aryl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperatures, forming carbocations and nitrogen gas. Therefore, in this unit, we shall discuss the chemistry and synthetic applications of arene diazonium salts, only particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrobenzene diazonium fluoroborate, and para-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride as determined from analytical data and molecular weight determination is C6H5N2Cl. Grease structure. Grease proposed structure 1 for benzene diazonium chloride in which both the nitrogen atoms were directly linked to the benzene nucleus. This structure, however, failed to account for the following facts. First, its salt-like character. Second, displacement of both the nitrogen atoms by a univalent atom or group in most of its reactions. Third, its reduction to phenylhydrazine in which only one hydrogen is attached to the benzene ring. Fourth, formation of azo compounds by coupling reaction. Fifth, formation of aromatic diazonium salt from penta-substituted anilines. Third, Kekulé structure. Kekulé proposed structure 2 for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleons. Evidence in favor. Structure 2 explains most of the drawbacks of grid structure 1, such as its reduction to phenylhydrazine, formation of azo compounds by coupling reaction, preparation of diazonium salts from penta-substituted anilines, and displacement of both the nitrogen atoms by a univalent atom or group. Points against Kekulé structure. Structure 2 cannot explain first its salt-like character and second its instability as compared to azo compounds since both contain nitrogen-nitrogen double bond linkage. Fourth, Blumstrand structure. Blumstrand suggested structure 3 for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objections of structure 1 and 2. Structure 3 is further supported by the following facts. First, its ready solubility in water but not in common organic solvents. Its complete ionization is shown by conductivity measurements. Third, the presence of a triple bond is shown by infrared spectroscopy. Fourth, its instability as compared to azo compounds. Fifth, it explains the geometrical isomerism as shown by diazotates or diazoates, which are the metallic salts of diazonium hydroxide. The sodium benzene diazotate can exist as a pair of geometrical isomers due to hindered rotation about the nitrogen-nitrogen double bond. Preparation of diazonium salts. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrate to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. Primary amine plus NaNO2 plus 2 moles of HX at 273 to 278 Kelvin gives arene diazonium salt plus NaX plus 2 moles of water. Diazonium salts are also formed when aromatic primary amines react with nitrite esters such as amyl nitrite. The nitrite esters needed for the purpose are prepared by treatment of alcohols with nitrous acid. This process of conversion of a primary aromatic amine into its diazonium salt is called diazotization. General procedure for diazotization: the primary aromatic amine is dissolved or suspended in its dilute acid such as HCl, H2SO4, etc. 3 moles of the acid are generally used for every mole of the amine benzene diazotized. 1 mole to form the salt of the amine, 1 mole to liberate nitrous acid from sodium nitrate, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reactions. For a coupling of the diazonium salt is formed with the free amine. The amine solution is cold and cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as a drop of the reaction mixture produces a blue color with starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since subsequently interfere with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperatures, they are used immediately after preparation. Evidence in spot. This mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophilicity of the amino group is reduced due to the electron withdrawing effect of the NO2 group as shown below. Such amines can, however, be diazotized in acetic acid. Conversely, aromatic amines containing electron donating group at ortho and para positions, example orthotoluidine, para-azidine, undergo diazotization much more readily than aniline. Stability of diazonium salts. Aromatic diazonium salt are much more stable than aliphatic diazonium salts due to the dispersal of the positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocations. Since the phenyl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salts have much lower tendency to eliminate nitrogen than aliphatic diazonium salts. In other words, aromatic diazonium salts are much more stable than aliphatic diazonium salts. Physical properties. Arene diazonium salts are generally colorless crystalline solids, highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salts such as fluoroborates are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complexes with metallic salts such as zinc chloride, example Arn2 positive whole twice ZnCl2 negative. These complexes are generally insoluble. Chemical properties. Arene diazonium salts are highly reactive compounds. Their high reactivity arises due to excellent leaving ability of the diazo group as nitrogen gas. They are therefore extremely useful synthetic reagents in organic chemistry. The reactions of diazonium salts are broadly divided into two categories. A. Reactions in which the diazo group is replaced by monovalent atoms or groups. B. Reactions in which the nitrogen atoms are retained. A. Reactions in which the diazo group is replaced by monovalent atoms or groups. Some important reactions of this category along with their synthetic applications are discussed below. First, replacement by hydrogen deamination. The replacement of the two diazo group by hydrogen or the reduction of diazonium salt to arenes is usually brought about by treating the diazonium salt with hyperphosphorus acid at room temperature, preferably in presence of copper 1 salt as a catalyst. This reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing reagent. Alternatively, diazo group may be replaced by hydrogen by adding arene diazonium salts with ethanol. For example, arene diazonium salt plus ethanol on heating gives arene plus nitrogen plus HX plus CH3CHO. This whole process involving the diazotization of an amine followed by reduction of the diazonium salt as replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salts with ethanol, two products are rarely obtained, with one involving the replacement of the diazo group by hydrogen as discussed above and the other by the ethoxy group. The relative amounts of the two products, however, depends upon the nature of the diazo compound and the alcohol used. If A I group is present in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominates. If, on the other hand, methanol is used, the predominant product is aryl methyl ether. Anisole. Mechanism. Synthetic application. The importance of deamination is illustrated by the following applications. First, synthesis of metabromotoline. Paratoluidine, when it's undergoing the process of acetylation, gives para-methyl acetanilidine, which further on bromination gives 2-bromo-4-methyl acetanilide, which on further hydrolysis using 70% H2SO4 on heating gives 2-bromo-4-methyl aniline, which on further diazotization gives diazotization product, which on deamination gives meta-bromo Toluene. Recall, meta-bromotoline cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation on bromobenzene due to ortho-para-directing nature of the methyl group and the bromine atom. Second, synthesis of 1,3,5-tribromobenzene or symmetrical tribromobenzene. Aniline on bromination gives 2,4,6-tribromoaniline, which on further diazotization gives diazotization product, which on further deamination gives 1,3,5-tribromobenzene. Third, synthesis of 3,5-dibromotoluene. Paratoluidine on bromination gives 2,6-dibromo-4-methylaniline. On further diazotization gives diazotization product, which on further deamination gives 3,5-bromotoluene. Recall direct bromination of toluene with Br2 FeBr3 gives 2,4-dibromo-toluene. Second, replacement by hydroxyl group or synthesis of phenols. Diazonium salts react with water in presence of acid to form phenols. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. The acidic conditions minimize the side reaction involving the coupling of phenol with diazonium salts. This reaction occurs by SN1 mechanism. Synthetic applications. This reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. Synthesis of metanitrophenol. Metanitroaniline on diazotization gives diazotization product which on Boiling gives metanitrophenol. Third, replacement by halogens. Different methods are used depending upon the halogen to be introduced. First, replacement by chlorine or bromine, Sandwich reaction. Aryl chlorides and bromides can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride and hydrochloric acid or cuprous bromide and hydrobromic acid. This reaction is called Sandwich reaction and gives aryl halide in 60 to 80% yield. For example, benzene diazonium chloride on addition of CuCl in the presence of HCl gives chlorobenzene, or else benzene diazonium chloride on addition of CuBr in the presence of HBr gives bromobenzene. It may be noted here that it is the halogen which is attached to copper which enters the nucleus. Sand mechanism of Sandwich reaction is believed to occur by free radical pathway. Gattermann reaction. It is a modification of the Sandwich reaction in which copper powder and a hydrogen halide are used instead of copper halide dissolved in the corresponding hydrogen halide. Yields are often lower, around 40%, than those obtained by Sandwich reaction. Synthetic application synthesis of 1,2,3 tribromobenzene. Para-nitroaniline on bromination gives 2,6-dibromo-4-nitroaniline, which on diazotization gives azotization product, which on doing Sandwich reaction gives 3,4,5 tribromonitrobenzene, which on addition of SnHCl and NaNO2 in the presence of HCl gives 3,4,5 tribromobenzene diazonium chloride, which on deamination gives 1,2,3 tribromobenzene. B. Replacement by iodine. The replacement of the diazo group by iodine does not require cuprous halide or copper as catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodine in potassium iodide. Synthesis of para-iodonitropentane. Para-nitroaniline on diazotization gives diazotization product which on addition of I2 in the presence of Ki gives para-iodonitropentane. Say replacement by fluorine, Wahl-Simon reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid (HBF4), diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salts, diazonium fluoroborates are fairly stable compounds. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. For example, this. Synthetic application synthesis of fluorobenzene. Aniline on diazotization gives diazotization product which on further addition of HBF4 gives benzene diazonium fluoroborate which on heating gives fluorobenzene. Fourth, replacement by the cyano group. Synthesis of nitriles. Aryl nitriles can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the lysocyanide as HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandmeyer reaction. Synthetic applications. Since hydrolysis of nitriles gives carboxylic acid, therefore, synthesis of nitriles provides us with an excellent method for the preparation of carboxylic acid from nitro compounds. For example, toluene on nitration gives para-nitrotoluene, which on reduction in the presence of HCl or NaOH gives paratoluene, which on diazotization gives diazotization product, and then it gets neutralizes with Na2CO3 and on addition of CuCN gives para-toluenitrile, which on hydrolysis gives para-toluic acid. Fifth, replacement by the nitro group. Nitro compounds are generally prepared by treatment of diazonium fluoroborate with an aqueous solution of sodium nitrite in presence of copper powder. Benzene diazonium chloride on addition of HbF4 gives benzene diazonium fluoroborate, which on addition of NaNO2 in the presence of copper gives nitrobenzene plus nitrogen plus NaBF4. Sixth, replacement by an arsenic acid ASO3H2 group, that is part reaction. Treatment of an arsenine diazonium salt with sodium arsenic in presence of copper sulfate followed by acidification gives an aryl arsenic acid. For example, benzene diazonium chloride plus arsenic acid in the presence of CuSO4 gives gives phenyl arsenic acid. Seventh, replacement by an aryl group, Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound in presence of an aqueous alkali, biaryls are formed. Yield are usually less than 40%. For example, para-bromobenzene diazonium chloride on addition of benzene in the presence of NaH gives para-bromodiphenyl plus nitrogen plus HCl. Reactions in which nitrogen is retained. First, reduction of two aryl hydrogens. Arene diazonium salts upon reduction gives good yields of aryl hydrogens. This reduction can be brought about by a number of reagents such as stannous chloride hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. If, however, strong reducing agent such as Zn in the presence of HCl is used, the product is an aromatic amine. Coupling reaction. Arene diazonium salt reacts with highly reactive, example electron-rich aromatic compounds such as phenols and amines to form brightly colored azo compounds. This reaction is known as coupling reaction and is extensively used in azo-dye reaction industry. Whereas coupling with phenols occurs in basic medium, that of amines occurs in faintly acidic medium at 273 to 278 Kelvin. Coupling usually occurs at para position with respect to OH or the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. For example, benzene diazonium chloride plus paracresol on addition of OS negative at pH 9 to 10 gives 2-phenyl azo 4-methylphenol. If a compound contains both an amino group as well as a hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. For example, para-aminophenol on addition of benzene diazonium chloride uh, and OS negative at pH 9 to 10 gives 4-amino 2-phenyl azophenol, and whereas in acidic medium it gives 4-amino 3-phenyl azophenol. The well-known indicator methyl orange, which is widely used in acid-base titrations, is obtained by coupling the diazonium salt of sulfonylic acid with nitrogen-nitrogen dimethyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of aromatic, sorry, electrophilic substitution reaction in which diazonium ion acts as the electrophile while phenol or amine acts as the nucleophile. A. Coupling with phenols. Since benzene diazonium ions are only weakly electrophilic, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide anion is strongly nucleophilic, therefore coupling reactions of phenols are usually carried out in an alkaline medium. Role of pH. The pH of the medium plays an important role in the coupling of phenols. As stated above, coupling of phenols is carried out in the weakly basic medium as explained below. Above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to diazohydroxide, which further reacts with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium as shown below. Since at high concentration of OS negative ion, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B. Coupling with amines. First, tertiary amines. The mechanism of coupling reaction of diazonium salts with tertiary amines is similar to that of phenols, except that this coupling is carried out under weakly acidic medium. Reaction with primary and secondary amines. Coupling of diazonium salt with primary or secondary amines occur in neutral or mildly alkaline medium. Here, anisotropy group of the amine first attacks over diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoaminoazo rearrangement to form para-aminoazobenzene by the following mechanism. Role of pH. In the presence of a high concentration of hydrogen ion, the lone pair of electrons on the nitrogen ion accept a proton. As a result, the amine exists predominantly in the protonated form as shown below. Due to the absence of a lone pair of electrons on the nitrogen atom, the amine is no longer nucleophile and since the coupling reaction will not occur at high concentration of H positive ion, example low pH. Further, as explained above, too high alkalinity will also not favor coupling reaction by forming unreacting diazohydroxide or diazotate salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for such coupling reactions. That's it for diazonium salts. Thank you for watching.